So, like, rather than think of a formulaic way to do this, right, we have a few options. We can try, draw a visual representation. Okay, and we can think, how can I fit 13 things into here, maybe? Because you know that in your situations, how do I know what the actual pigeons and pigeonholes are? Because that was one of the things you want to do. I want to try and identify those first. What condition do you know from the pigeonhole principle to identify those? There's a relationship between the number of pigeons and the number of pigeonholes, right? For this to be true, your n has to be bigger than your k, right? The number of pigeons that you have has to be larger than the number of pigeonholes here. So when you look at a question, you immediately know which ones are your pigeons. Well, it's how many times you're throwing them. What's your pigeonholes? Yeah, it's what you can actually roll, right? And so when you think about it this way, okay, another thing you realize is that the pigeonhole principle simply states that, okay, you must have at least n over k, yeah, in at least one. Sorry, Harry. So when I know that I have n equals to 13 throws, I might just put pigeons in brackets there, and k equals to 6 numbers, and those are my pigeonholes. Then how can I work that out formulaically? What can I do with this? I've identified the pigeons and pigeonholes. How can I work out how many is the least number of times a number must turn up?
n minus 1 over k plus 1.
So interestingly, right, we can try and think about this reversal process. But what is the pigeonhole principle saying? Yeah, because the pigeonhole principle says that if I just have n pigeons and k pigeonholes, right, at least one of the holes must have at least n over k. That's actually what it's stating. So go back to that. You can use that, right? If you're not asked to justify your answer, this is something that you can use. So there has to be at least, well, in this case, what's that? 13 over 6. Can someone calculate that for me? What is that?
Like 1, 2, 2.
Why would I use the exact answer?
So 1 wants to 66. Okay? And then that way, I know that, oh, okay, well, remember, I can't have 2.166 die. I have to say, that means that there's at least 3 die in at least one. And that works out, right? Because if you think about worst case scenario, this is what you got. And then one more, well, there has to be at least 3 if I'm assigning it that way. So what's another situation we could try? So 14, the answer should still be 3. Would that be correct? If I change this to 14 pigeons, if I change it to 14, I'd have an additional 1 here. Let me go back to this one, right? Can you see if I add an additional 1, does it change the actual answer I get? No, it doesn't. If you do 14 divided by 6, what is that? It's 2 point something, right? Just because I add an additional 1, it doesn't change what is the least number of times a number must turn up. How do you get to a higher value? Well, you have to fill up again all of these, because we're talking about the worst case scenario. You have to fill up all of these. That was a loud bang.
Yeah, the door closed.
Okay. You have to fill up all of these until you can't fill them up anymore, and only then does it guarantee that there's at least that number of times a number turning up. Does that make sense? Right? That's the idea behind the pigeonhole principle. We're looking at the worst case scenario to guarantee this situation. And in order to work out how many the least number of times the number must turn up is, we can use n over k in order to calculate that.
You could use the lowest thing.
Does it work?
You'd have to just round like down instead of up.
Yeah, so I think there are actually different formulas that exist for this, but I think it's much easier to just think about it logically and work it out that way. Call upon your n over k, make sure you're justifying your answer if you need to, but that's kind of how we can get our head around how to respond to these different types of questions.